Hi to everyone and welcome to this Maya Heat Transfer Technologies webinar. Okay, right now I'd like to introduce today's presenters. First up today we have Charles Susu. Charles is the Technical Manager for Maya Heat Transfer Technologies. He has over 10 years of experience consulting companies on how to optimize their engineering solutions in simulation, PLM, 3D scanning, and overall manufacturing. A mechanical engineer from Concordia University, his specialization is in design and manufacturing for aerospace. Okay, also with us today is Angelo Flemings. Angelo is the Vice President of Global HEADS Portfolio Development at Siemens Product Lifecycle Management Software. Flemings has over 30 years of experience in high-tech software, product design, engineering, manufacturing, and testing in various industries. So, gentlemen, welcome to today's event. And with that, I'm going to pass things along to Charles to get us started. So, Charles, go right ahead.
Hi, everybody, and thank you for joining us for today's webinar. Discover better designs faster, driving product innovation through design space exploration. My name is Charles Susu, Technical Account Manager at Maya Heat Transfer Technology, and I'm here with Angelo Flemings, Vice President of Global HEADS Portfolio Development at Siemens Product Lifecycle Management. In the last century, we've all witnessed evolution on a personal level. If you take a look here, Easter morning in New York City, you're going to spot an automobile. And if we take a look 13 years later, you're going to spot a horse, and there's automobiles everywhere. This is the Vatican in 2005. What do you see on the bottom right? A person with a flip phone. Let's take a look 8 years later. You're going to see one person with an iPad and everybody else is with a regular phone. The rate of change is incredible, even in our own industry. Now that I've shown you the effects on a personal level, let me show you the effects on a global levels. From mechanical components to smart systems, integrating mechanical, electrical, and controls. Now you can't just have a basic mechanical product. Everything needs to be connected. Now when we're looking at material and production methods, that's changed to mixed materials, novel product methods, additive manufacturing, composite with high-strength steel and aluminum, all done in one production. From defined options to mass customization and personalization, you can't just pick one product anymore. Every product needs to be customized to that person. And finally, from just standard internet connectivity to systems of systems and Internet of Things, everything in today's world is connected. By 2020, the global volume of data will soar to 44 zettabytes and 50 billion devices. Siemens recognizes this, and for the past 10 years, they've invested $10 billion acquiring different parts of the digital twin. Siemens has created the Digital Innovation Platform. This is where they have all the parts connected by a digital thread to create the digital twin. Everything from the mechanical, electrical, software, simulation. Also on the other side, you have manufacturing, automation, execution, and analytics. And all of this platform is connected for collaboration in Open IoT, which is Internet of Things. And today we're going to be talking about an integral part, which is performance analytics. And this is the HEAT software where it can connect everything inside the digital platform and optimize it. And using that optimization, you'll be able to discover better designs faster. Maya is an integral part in helping companies adapt and lead this paradigm shift, and we've been doing this for 36 plus years. We have over 180 engineers and scientists, all working in predictive engineering and digital simulation. We also have a segment doing custom engineering applications and software. Another segment is engineering services. And we develop 35 of the products that's inside the Siemens PLM portfolio. Outside of that, we also develop artificial intelligence, Internet of Things, And we also do integrations of products like the CAD, CAE, CAM, and PLM. Also process automation, and finally, product lifecycle management. Here are some of the elements that we help our clients with to optimize, adapt, translate, and evolve in a rapidly changing environment. We help in the design phase, in the simulation phase, product lifecycle management phase, integration and automation, and this works out not just in the simulation of the CAD part, but also your entire workflow. Real-time test data integration. This is things like data centers, where things are changing all the time, and you need to understand what that means and how you should change things. Manufacturing. This is where you hear Industry 4.0, and this is where the world is moving forward. And finally, artificial intelligence. This is where we said before, there's a huge amount of data now, and we need to leverage this data to understand what's going on and make better decisions faster. And now I'm going to leave it off to Angelo, where he's going to be telling you about the great product that he has, HEATS, where it allows you to discover better designs faster. Angelo, all yours.
Charles, thank you very much for the kind introduction. We are especially pleased to have Maya as a partner from so many perspectives. Obviously, you guys are the maker of outstanding software products that we are reselling. In addition to that, you provide outstanding level of engineering support, helping customers to take the technologies that they've purchased and apply it to problem solving. What we're going to now focus on is how we can help our customers to discover better designs faster. And the key there is right in the title. It's assisting them to come up with innovative designs, not just making small tweaks and changes to designs, but coming up with new, exciting products that the consumer loves. And the way that we accomplish that is through something we call design space exploration. And you'll note that it didn't say optimization, but design space exploration. And we'll talk about the difference in those terms or words here shortly. But here's something that's just real, is as identified by many of the CEOs of top companies, Fortune 500 companies, they are tasking their organizations with driving greater innovation. Well, what's that all about? And why is there a need for that? Well, we have educated consumers now. So our consumers are expecting for us to have products that are customized to the things that they like, whether it's a certain look or feel or color or style or behavior. And we are also letting them know that we will deliver these products to them in less and less time frame. Why? So that they have a competitive advantage or they have something that's unique that their neighbors don't have. Well, these become boundaries, constraints, or challenges for companies. That we're helping companies to get through this challenge. That is, to have robust, exciting, state-of-the-art, or industry-leading products in less time. It's through design space exploration. Here's an example of a printed circuit board. The objective of this printed circuit board is to take this baseline design, make it way less, and also to improve the cooling efficiency. Well, our software product called HEATS will automatically work or drive our simulation tools that capture all of these physics. So it's going to automatically make changes to the CAD model. In this case, it might be the location of the cooling fan at the top or the actual location of the exit vents on the bottom of the model. It will also change the shape, the size, the number, and the material of the cooling pins, and then allow us to drive our analytical tools that represent these particular characteristics in simulation in this automated fashion to figure out which combination of variables or variable changes will give us designs that meet our objective on a broad scale. Again, directly changing the simulation tools that we're already used to working with. The result of this effort is just in a few hours. HEATS is able to produce a new design that is significantly different than the baseline design, that is the number of pens, their orientations, etc., that reduces the overall mass by 51%, while improving cooling efficiency by 25%. So, what's going on with this whole design space exploration thing? Is it something that just one industry is using? The answer is no. Design space exploration is something that's been really well received in the automotive industry, where they have problems such as this cooling jacket problem, where there's 24 different holes in a very highly constrained area, and they're looking to find out what's the optimum size and shape and location to improve cooling efficiency of their engines. Or, for instance, in oil and gas, where we've got these big, large platforms, and it's important to ensure that the platforms are properly oriented in the sea, so that in case there's a catastrophe, the lifeboats are drifting away from the platform versus towards the platform. And it competes with things such as the orientation or placement of the helideck and the smokestacks, because the smokestacks are getting rid of different chemicals and products, and we want to ensure that the smoke itself is not interfering with the helideck, the lifeline from the platform to land, bringing people and product back and forth. These complex problems today are being solved with simulation models, but some of those techniques take a long time. What we're doing is we're helping, that is with HEEDS, to really amplify the value of the simulation that they have or the investment that they've made. HEEDS is really helping them to redefine how that they are deploying tools and methods to come up with innovative solutions. And it's doing it this way. Well, let's just first kind of compare how people are leveraging simulation today. Well, it's mostly in a reactive mode. We take our CAD models and we take our CAE tools, and we're trying to maybe fix a field failure. So we're changing some values and parameters around, and we're then looking at the results and saying, is it better or not? And because of time, we often don't have an opportunity to do as much proactive probing to see what innovative or new solutions may be available to us. So this is primarily what folks are doing today with simulation tools. But HEETS is adding this new value of automating the process of changing our math-based models, changing those parameters automatically, and exploring the space broadly in a fraction of the time it would take us to make manual verifications and assess those changes. So it's just a really neat thing that's happening here. That is us being able to take simulation to another level. Let's just do a couple comparisons of how we see people problem solving today to reinforce the value of this heat space technology. And I've already mentioned that we're typically doing simulation for a couple of reasons. One is to fix a field failure, or it's to come up with some new design. And we often are referencing a baseline design or part that we already have in our catalog or our library. So what the engineering teams and design teams are doing is often the design teams come up with a new variation within the CAD model or CAD tool of their choice, and then they send that design over to the CAE team. They put meshes on it. They run structural analyses on it after applying, obviously, the load cases and such. And then they potentially will run a CFD analysis on it. It calculates these responses, and then they say, well, I'm not sure if that's what we're looking for, if we met our performance targets. And this trial and error process is just hard. And it's becoming harder and harder every day. Why? Well, because our systems, our designs are becoming harder and harder every day. For instance, we have this thing called additive manufacturing, where we're using 3D printers to make new designs, new organic shapes. And included in that are often electronics. So we've got this layer of structure and electronics being integrated together at one time. We're even adding software to things, which is yet another series of variables and things that have to interact with the whole structure, systems, or parts. So we just have challenging designs. It's been known that the human mind can keep track of 2 or 3 variables at best, and often our designs have tens, if not hundreds, of variables. So what we want to do is make sure that we realign the deployment of human capital, of our software and our hardware assets. And it's spending less time building and manually sort of searching and doing tests, and automating that process. The human is better not just making these mundane changes, but accessing the information given from the simulation models. And the way that we help that process with HEADS is through these 4 enablers or pillars. We've already talked about process automation, that is directly driving the tool or tools that we're using on a day-to-day basis. But instead of making manual changes, again, automating this process, leveraging whatever compute resource that we have or resources that we have. Some software is best run on Linux-based machines, others on Windows-based machines, others in the cloud. HEADS will manage any combination of these assets for us on unlimited cores. And then we have intelligent search that we're coupling with that allows us to solve these complex problems in less time, especially significantly less time than the manual method, but less time than any other approach that's available to product development teams. And then most importantly, we kind of put a nice little spin on it and call it insight and discovery for those who are old school, post-processing, looking at graphics, looking at tabular information and plots, and really get insight as to how and why a design is performing better than maybe the baseline design. So for HEADS, the first step is we have to identify some math model, some parameters that HEADS will be able to change. For this example, we're showing that we have a validated CAD or CAE model. The first step for HEADS is then from left to right to create the workflow of the tools that capture the physics that we want to change. So we will make geometric changes to this cooling model, this electronics model in NXCAD, and then HEADS will handle sending that new geometry into, in this example, StarCCM Plus, where it regenerates the model, it adds the mesh, applies the loading conditions, solves the problem, and then feeds that information over to our costing model. What's that all about? Well, more engineering teams globally are also asked or tasked with calculating costs. Why is that? Because upper management is not going to say, hey, we'll settle for small to no margins on this one design concept that you're presenting. So cost for us can be a response we're calculating, or it can be a constraint that says any design above this price point, stay away from. So that's going to affect how he searches the space to find feasible solutions. The next step is for each one of the software tools that we have in XCAD, we let HEADS know that more than likely we're going to run that on our local Windows-based machine. But for the CAE tool or StarCCM Plus, we're going to operate that on our local Linux-based cluster, or perhaps it's a cluster on the other side of the world, or even a cloud-based resource. As long as we can gateway or link to those computer assets and licenses, HEADS will drive that for us and manage that for us automatically. And then perhaps the window or the costing model is on another Windows computer in the finance department that we're going to tap into or leverage. Now, having set those two things up, the next step for HEADS is simply to say, what are the variables that we want to change, their type and their ranges? What are the responses that we want to calculate? And then what are the constraints or requirements? And having said that, HEADS can then go about searching the space to find feasible solutions, either for a single objective study where we're looking at just one objective, I want to find the lowest mass design, or a multi-objective study where we have 2 or more competing objectives and we're going to have a Pareto front, a family of good designs along the curve. And while HEADS is running, we can either post-process the data or look at the data in real time, or we can wait till the study's done to gain insight and discovery, to understand what makes a good design. And so steps 2, 3, 4, and 5 is one HEADS license. Again, a license that runs unlimited software tools in any workflow or on unlimited resources. And so again, there's so many things that HEADS is leveraging. If we look at just parametric modeling by itself, whether it's parametric CAD and such, we now can take and create all sorts of interesting shapes with this automated fashion and have confidence that the CAD can regenerate the model. The same thing is true with auto meshing technologies. That just continues to get better and better. So this having confidence in this automated method is something that, again, continues to get proved year in and year out. But for this particular example that we're showing, another cooling example, please note that on the x-axis we have the average chip temperature, and on the y-axis we have pressure drop. In this study, heat is found, and there's that Pareto front, that curve along the bottom. All the best designs representing the trade-off between the temperature and pressure drop. So what does this mean? This means that when we go into an engineering meeting, we now can have a solution for our customers. If they say we can live with a temperature of 120 C, we simply go up with our mouse, we click on the dot that is close to the 120 C temperature or the dots in that area, and we see the images, all the engineering data, graphs, tables, etc., defining the performance, the optimum performance of that particular design. And we can have intelligent discussions on manufacturing and deployment. So that's really what's happening here. HEATS is allowing us to speed up, significantly enhance the old process of manually changing designs to find a better solution. So what is it doing? Let's take a look at this bumper example done for a company called Magna Technologies. They wanted to also participate in helping to improve fuel economy, and so there was a lightweighting effort done on this bumper system. It's automatically changing the shape, and we're focused primarily on the crash cans. There's two of those that go behind the front end of the bumper there. And there's a parameter for the width, the height, and the length of the crash can, along with a parameter for something called the crush initiator. There's a little dimple there that HEATS is moving along the different surfaces there, or removing entirely or changing the shape of. From there, it changes the CAD. It feeds that into the crash analysis software. For this particular example, Magna Cosma uses the LS Dyna software tool. And then there we're calculating the intrusion of that particular design concept and repeating that process. The results of that is that HEATS is able to find a design, or actually a series of designs, that reduce the mass by 32% while satisfying all the government mandated crash requirements. This again is innovation, not looking at small scale changes of an existing design, but really searching the design landscape to find new exciting solutions. Now we're going to compare HEATS to something we call the traditional approach. So some software companies some product companies, development companies out there have bought software tools that are what we call optimization-based methods. And those optimization codes are often leveraging local methods such as design of experiments or response surface methodologies. So what's the process for them to figure out how to change something to get a better solution to calculate new performance? Well, they start off with a baseline design. But since these methods don't like lots of variables, it's up to the user then to screen the variables. So we're going to look at the baseline design and say, here are the 3, 4, or 5 parameters. We usually want to do 10 or less if we're using DOE methods that are affecting performance of the baseline design. So we're going to focus on a handful of those. We have a long list of algorithms, maybe 50 or 60 to pick from, that are defined as global or local methods. Each one does something differently, so we kind of have to do our research on that or go with Old Faithful, our favorite. They don't run by themselves, so we have to then tune those algorithms. We conduct the search, we get the answer, and realize that the answer we have is different than we want it. And if you notice at the top, the arrows are going backwards because this process is one that then has to be repeated, where the user is responsible for maybe changing the variables that they're using, or the algorithm that's being searched, or how they're tuning the algorithms. This again was state of the art about 18 years ago, and it gave us 1 to 7% gains, but it is, and you see the reactions from customers, error prone, costly, difficult, and simply put, only used for the toughest optimization problems by optimization experts, a process that was not deployable to the masses. So what's the difference between Heats and this traditional approach? Well, first of all, Heats also has all those local methods, but we're doing something differently. As previously mentioned, we take the baseline model or models, and Heats is directly changing all of the variables in the simulation tools that capture all the physics that we want to modify to come up with either a better solution, moving away from obviously the baseline design, or one that fixes the baseline design in the case of a field failure in less time. And everyone now can use it. Why is that? Because again, there's no need to do variable screening. We simply have our workflow and we let Heats know which variables we want to change, their range, their types and ranges, the responses we want to calculate, how long it can run, and it searches the space more efficiently than any technology available today. And also, we're not exchanging speed for accuracy. What do we mean by that? Well, we've often already validated our CAD models or our CE models. And in this approach, what we're actually doing is driving those validated models, all the parameters, the same parameters that we're measuring on the bench, the same parameters that we're changing in the field, we are changing in our simulation engine. There is no limit to the parameters that Heats can change because we're driving the simulation tools that capture all those physics. It's just a smarter, modern way to search the space, relying on models and tools and processes that have been validated. Once we have good designs, then we can select those designs and say, now I'd like to apply the local methods where they're best served. That is to do things such as looking at the sensitivities of variables, not on the baseline design we're moving away from, but on the new design so that we can create manufacturing schedules, maintenance schedules, etc. So this process is faster, easier to use, modern, and more accurate. It helps with the realization of what we refer to as the digital twin. Here's an example that we like to use to illustrate the value of, again, this approach versus the traditional approach, and it's an underhood pipe flow model. The objective is simply this, is we want to improve the flow uniformity on the outlet side of the engine. So close to the engine block, you will see the hose, that's the input side of it, and then closer to us is the output side of it. So what are we doing here? Well, we want Heats to change 7 different variables, a cross-section center, a radii, and angle, to improve the flow uniformity. And after 24 hours of running on a cluster, Heats was able to find this design concept you see in the center, which improved the flow uniformity by 30%. But if we look at it, it's a non-intuitive shape. Most engineers would not put that sort of transition, if you will, into the holes. But this is the out-of-box thinking that technology allows us to do today. So we take a look at this design and we say, this is really, really cool. I like where it's going here. But for this application, I'd rather not have swirl. And if we see in the image in the center, there's a swirl condition that is a resultant of this new shape. And we can also look to the image to the right under visualizing behavior and see how that swirl was introduced with this new set of geometry. So what do we do with this? Well, it's real simple. With the Heats technology, we simply say, you know what? We're going to add a constraint that says we want to reduce the swirl, and we're going to continue to run for another few hours, for 5 more hours. And in less than 48 hours, we now have a design that is once again a non-intuitive shape that improves the flow uniformity by about 30% and decreases the swirl by 50%. So this is really what we want to do with our simulation technology. We want to search the space, find new non-intuitive shapes, learn from them, because the human mind has the capacity to do that. See that sometimes there's other conditions that we might want to address that allow us to then take this new concept and make it manufacturable and robust. All of this being done with the same facility, the same tool, on the same models that we've already come to know and trust. If we take a look at this next slide, we'll see something interesting in this Pareto front. It has this sort of jump or curve, and we've circled that in red, a leap, if you will, or step that we're looking at. It's an unusual shape. That's where we want the engineer to concentrate their time to say, why do we see that knee or jump? And I'll answer that question now. We look in the lower left-hand corner, we see that the design there that's called the best design has a sort of a longer transition shape from the outlet side going back towards the inlet side of the engine. If we look to the far right, we'll see that there's another family of designs that has more of a 90-degree bend or transition. So this allows us to explore different design concepts to figure out which one is easier to put or assemble into our actual product. Knowing all the behaviors as well, which is most importantly, or performance criteria that we get with each one of those considerations. Now let's take a look too at this plot that we created. It's called the response influence plot, and the focus is on outlet swirl. And remember, what we're doing here is we're doing really a comparison with this Heats approach versus what we were calling the traditional approach, which is often based on design of experiments or DOE. If we look at the blue, we'll notice the 7 parameters on the x-axis that influence the outlet swirl. R2, X2, and X1 are the 3 key variables that influence outlet swirl on our baseline design. So if an engineer is going to use design of experiment, more than likely then we're going to get rid of all the variables that are not influencing the outlet swirl on the baseline design, which means we would get rid of Y2, R1, Y1, angle, and maybe even X1 because there's just a small influence on, again, X1 as it pertains to outlet swirl. If you want, let's throw it in, okay? What would happen? Well, what would happen is we would get some gain. But if we look at the best design that Heats found, R2, X1, and angle are the 3 more important variables influencing outlet swirl. If we got rid of angle using DOE, there's no way in the world it would be considered and giving us a unique and innovative and better design. You can't change what's not there. So what's the moral of the story? The moral of the story is simply this. When we include all the variables that influence performance, this is what helps to facilitate innovation. Allow the software, this intelligent search, to figure out how to move these variables around to give us innovative, new, robust designs. And we've got lots of plots and functionalities that help us to understand what are the key sensitive, the sensitivities of the different variables that we might want to consider from a manufacturing perspective. And in the plot here that we're showing, we want to concentrate on the dark red colors and the dark blue colors because there's either a strong positive or negative correlation between our variables and these particular behaviors. We'll learn more about that when you actually contact Maya for a demonstration. So let's go on to the third sort of what we call pillar there. We've talked about process automation. We've talked about distributed execution, working on whatever compute resources that we have or that we might want to include into the simulation. Now we're going to talk about that intelligent search engine. What are we doing here? Well, for those who have an optimization background, we're looking for the highest peak or the lowest valley, the strongest design, the design that weighs the least amount. So we're looking for the highs and the lows. Now, the challenge is the following. The challenge is if we're using a local method, we get locked into a method and we have to search this unseen design landscape. And as we're searching the space, in this example of, again, climbing up and down a mountain, there are different things that we see at different stages, whether there's deep snow, whether the face of the mountain is steep, there's loose gravel. And for each one of these stages, what we really need is different equipment so that we can search and get up and down that particular section safely. What's best to have is a Sherpa, a guide, someone with the experience and the knowledge that helps us to safely traverse up and down the mountain. And what we're providing in simulation is exactly that. Something that's not locked into a method that crashes because it wasn't able to adapt as it's going from step to step or stage to stage. So this modern approach is an approach that's both hybrid and adaptive. Meaning what? It's a blend of many different strategies run simultaneously. It's always doing and uniquely doing a global and local search at each step of the way. Again, leveraging the strengths of each of the different methods, whether it be a gradient-based method or simulated annealing or particle swarming, or all these known types of methods, leveraging those in a unique way. In what way? Well, as it's searching the space, depending on how much time we give it, it's adapting its search strategy so that it's very efficient at how it searches the space to give us an answer when we need an answer to meet our product deliverables. And this is very, very important. So what does it mean that we're not doing? It means that we no longer have to do variable screening. It means that we no longer have to do space sampling, surface fitting, model simplification, which deviates from, again, being able to correlate our simulation findings with test data, both on the bench and in the field. We don't have to select from a long list of algorithms and hope that we tune them correctly to get some results. This is the modern way to leverage design space exploration. This is HEEDS. So we'll take a look at a few different applications. Here's where there have been direct comparisons of this local method against the HEEDS approach. And the first example is this jacket gasket cooling situation. What are we looking at doing? Well, we're looking at, again, changing 24 gasket holes to satisfy the constraints that you'll notice. There's several constraints there. What are the results? The results are in 20% less evaluations, 200 versus 250 evaluations for DOE. HEEDS was able to reduce the pressure drop by 10% when compared to the single best design found using design of experiment methodology, and also reduce the maximum head temperature by 7%. Here's the other really big deal here. It didn't find one design, but it found 16 feasible solutions. Well, why is that important? Well, simply put, it's this, is that when you have 16 solutions, you've got 16 choices. You can figure out which one of the solutions or designs is less intrusive on your manufacturing processes and tooling. You can figure out which one is lower cost, and all of these designs are optimal. So we know that they're going to meet our performance objectives. This is what design space exploration gives us. Lots of information in less time. Here's an example of a wind farm. The objective is to properly lay out all of these wind turbines in such a way to where we can make sure we have the most efficient utilization of these assets. And there are constraints, being the terrain itself and the many different turbines working together. There's this thing called wake effects. So the location of each one of these turbines is especially important. HEEDS was able to increase the annual produce or yield, by 8.5% over the original design. And we can take a look at, again, that original design here on the left and the new and improved design. This is significant. What about in energy? Here's an example of a heat exchanger. For many months, this company was striving to get the crude oil at a certain temperature going through some sensors, electronics. They didn't want the electronics to melt or fail. And after 6 months of effort, weren't able to successfully reach that objective. HEEDS was applied. HEEDS is going back to process automation, changing in XCAD, the actual geometry of the heat exchanger, feeding that information into StarCCM Plus to run the computational fluids dynamics, search the space, and come up with different groupings of tubes, different configurations, and even different material choices. There were two, optimum designs being either in super duplex or Inconel. This means choices. And it was able to, again, reduce in just weeks what used to take months. Months of no success, weeks of success, leveraging the tools that we're all comfortable with using. So what are customers saying? Well, Trek Bicycle, they love this technology so much that they even for their new products are listing HEEDS as one of the tools used to develop these innovative solutions. They've got very complex bicycles using composites and other materials, lightweight, but they have challenges of absorbing the energy because we don't want the rider to be the source of absorbing the energy, because that way the rider will be too tired. But making sure that the structural requirements are met and that these bikes are aerodynamic. And these complex problems they've thrown over to HEEDS, and HEEDS is giving them good solutions that allow them to be the market leader. The same thing is true with industry leaders such as Pratt & Miller that has really two divisions. They have an engineering service group that provides concept vehicles for NATO, and they also provide globally motorsports engineering support for GM. Why are they using this technology? Because they used to use the traditional approach and had limited success. Now they have this technology that allows them to explore the space broadly and with confidence, not streaming or screening any of the variables. And then lastly, Becton Dickinson, a global leader in the biomedical industry. These folks are making sure that their syringes are comfortable for the user, that they're safe, that they're producing good results each time so that clients don't have to keep going back and forth to get blood samples, especially those that might have compromised immune systems. So in a nutshell, what's happening here? Well, innovative companies are extracting higher value from their simulation models by using the HEATS technology that allows them to leverage all the investment that they've made in simulation products and testing products, validating models, and using those as a position to move forward with to either have new and innovative solutions and products. What is this all about? Well, HEATS is helping them to change their strategies on how they're leveraging these simulations for driving innovation. And the bottom line is this: HEATS is enabling them to discover better designs faster, gaining market share, gaining reputation and leadership, gaining most importantly, producing outstanding products.
Okay, gentlemen, thanks so much for that great presentation. Charles Susu and Angela Flemings, we want to thank you for spending some time with all of us today. And we'd like to say a special thank you to all of our audience members for being part of this webinar event. Take care and have yourselves a great day.